All right, it's a good tech day today so far. OneNote didn't crash on me this morning, and all my shortcut keys worked. So that's always a good start. Um, the plan today is to cover 3.2 measures of variation. So starting to talk about uh, a different perspective on some different descriptive stats that we might be interested in knowing or presenting. Possibly start 3.3 on measures of position and then finish that up next time. Note that I did post a supplement on geometric mean and harmonic mean. I posted that. I think I posted it Saturday, but it was still marked as private or something on YouTube. So I think I finally fixed that Monday morning or Sunday morning. But since I got it up so late, the supplement on geometric mean and harmonic mean, and there were a couple of questions on the 3.1 homework on those topics, I just extended that homework a week. So that's open through this coming Sunday. It was originally set to be due yesterday, but I figured with this information being posted so late, that wasn't really fair to you guys. So that's extended through this coming Sunday. And the quote of the day today is from the Greek philosopher Epictetus, if I can say his name, roughly translated as conceit of knowledge gets in the way of learning. And I think this is something that we kind of see a lot today as people tend to form very quick, almost instinctive or gut reaction opinions on seemingly everything that comes across their plate. I think that's a little bit of the kind of like Facebook Reels, YouTube Shorts, like TikTok kind of culture that we make very quick decisions. And a lot of times once we make a decision, we kind of latch onto that decision. So if we're too conceited in our knowledge, we have trouble actually incorporating new information, new data that comes at us. And that's part of what the scientific method is all about, is saying, okay, let's try very hard to overturn the things that we think are true. And if we take that approach, sometimes that can be helpful at allowing new information in. Now, the flip side of that is we live in an information saturated world. What information should be trusted, right? If I overturn my hypotheses or question my hypotheses or theories about the world, anytime that I, have a new piece of information come in, no matter who or where it's from, that also is that's kind of a recipe for failure in the other sense, in the sense that I'm just always spinning my wheels. I'm never going to be able to actually come to a conclusion, make a decision, because there's always going to be some other goofball somewhere that comes up with some piece of information that I feel that I need to incorporate. A lot of people would say, oh, well, just listen to the experts, right? So don't worry about your Uncle Bob at Thanksgiving, whatever he tends to rant about things. So just ignore him, but listen to the experts. But all that has really done is kick the can on the question is, okay, how do we define an expert? Do we just define an expert as somebody who tends to say things that we tend to agree with? Well, that's kind of the same as letting no new information in. Do we define an expert as somebody who has some certain degree? Well, that's probably kind of an arbitrary measure. So this is not an easy question to answer in a very careful way, right? To answer in a way that if you wrote down a definition for expert, that somebody acting kind of, what would you call it, like in a devil's advocate kind of manner, wouldn't easily be able to tear down that definition. So I don't have so many answers as to how you should approach these questions, but simply stating that these are questions that maybe ought to be thought about, especially in light of our current world that's so information saturated, or data saturated, depending on how you think about it. We're doing all of these statistics. That's really nice. But as we kind of saw in section 3.1, for instance, we can choose from lots of different measures of center to report. Why would somebody report one versus the other measure of center? Sometimes there's a good reason, like say with the mode and qualitative data. Sometimes it's a little bit more of a gray area. Okay, so moving on to 3.2. Remember last time we talked about the measures of center. In particular, we talked about the mean. Oh, let me rewrite that. The mean, the median, the mode, and the mid-range. We talked about some other things like the geometric mean and harmonic mean and the supplement, the weighted mean, and lots of others. There are maybe just 2 or 3 general points that I want to make about measures of the center really quick before moving on to measures of variation. And one of these points is going to really tie directly into what we discuss about measures of variation, building up one of our measures of variation. So I wanted to just mention these couple ideas. And really what these come down to is really what is almost my definition of mathematics is the process of generalization through abstraction. So we have a bunch of different things that kind of work kind of like a measure of center. These all kind of attempt to answer the question, what does the typical data point or data value look like? And again, left as a very ambiguous, amorphous question because we want to leave open the possibility for different types of answers, different perspectives on this. So you might think that, statistician A came up with the mean and said, hey, I think this is a cool idea. And statistician B, the median, and somebody else, the mode or the mid-range or the geometric mean or whatever. And these are just different answers to the same question that are completely disjoint from one another, right? That's how it feels at this point. There's a really interesting idea, though, in that every one of these measures of center can be traced back to a common source. And that's something called more or less something along the lines of a loss function or an error function or something like that. So if I have, let's just call it M as some measure of center, and I have x1 through xn data points that I'm going to use to generate M, the measure of center, I could consider some function of the M minus xi's. Generally, we would think of a function that gets bigger as M gets further away from each xi. And I could sum this over I equals 1 to n. For instance, maybe my function is just the absolute value function. The further away my measure of center, however I choose to define it, the further it gets away from a given data point, the larger that kind of loss is, the larger that penalty is, in a sense, the larger this contribution to this sum is. So then this sum would look like the absolute value of M minus x1 plus the absolute value of M minus x2 all the way out to absolute value of M minus xn. The larger that M tends to be away from typical data points, the larger this sum is going to tend to be. So a good measure of center should be a number that's kind of pretty close to most of the data points, in this case, in the sense of the absolute value measure. I could also have used, say, something like a quadratic function, something squared. Again, the larger that the measure of center that I develop, M, however I choose to define it, the larger it tends to be away from most data points, the larger these squares are going to be, the larger these individual terms are going to be, and therefore the larger the sum is going to tend to be. I could define my function as something like the maximum. In other words, this might look like the maximum of m minus x1, m minus x2, m minus xn. And if I'm talking about a maximum, I mean furthest to the right, closest to positive infinity in some sense. So I probably want to slap absolute values on these. So we have things like this. Well, interestingly, if I'm trying to, so just to reiterate a point that I had said before, if I'm looking for a measure of center, if I want a measure that represents a typical data point, I want a number that is in some sense fairly close to most of the data points. I've chosen my function so that as that number gets farther away from a lot of the data points, the contributions to the sum go up. And this, let's just call it L, I don't know, this L gets larger. My goal here is to choose M to minimize L. In other words, I want to first decide what my kind of objective function in a sense is. Do I want to try to minimize absolute values of distances or squares of distances or the maximum distance between the measure of center that I'm going to use and the data points? That gives me something like a loss function for a given choice of M. And then I can choose to define M in such a way that it minimizes this. It minimizes the kind of, in a sense, average distance away from each data point. This actually seems like a pretty reasonable general approach to answer the question, what does the typical data point look like? Or if I wanted to present to you a number that's representative of the typical data point, that number probably ought to be close to as many data points as I can make it, where close to is defined in the sense of maybe an absolute value or a square or a maximum distance. So if I choose an M in the first case to minimize this sum of absolute values, this actually yields the median. If I choose M to minimize the sum of the squares, this yields the mean. If I choose M to minimize the maximum, a minimax problem, minimizing the maximum distance, this yields the mid-range. There's kind of a similar idea for the mode. It's a little more abstract, but still related to this idea. The geometric mean, it is the mean of the logged data, which I discuss in the supplement. The harmonic mean is the mean, or well, it's 1 over the mean of 1 over the data. Again, discussed in the supplement. The weighted mean is actually a generalization of the regular mean. If all of my weights in a weighted mean were the same, if W1 equals W2 and so on up to equals Wn, then I just recover X bar, the mean. So the weighted mean is tied to the regular mean, but here we would just have something like W1, W2, and Wn in front of these little bits here. So our many seemingly completely different measures of center that we came up with really have this underlying theme of all of them minimize some kind of objective function like this. So there really is a common thread underneath all of these. And I think that's really one of the really interesting things about math and one of the really powerful things about math is it likely that the folks who came up with these initially all that they first looked at this objective function approach and then came up with all of them on that basis? Probably not. But probably what happened is they came up with 3 or 4 or 5 of them and then investigated those really thoroughly and realized, hey, there's this common thread that all of these things that we just kind of sensibly in a practical application setting came up with. We said these seem to be pretty reasonable answers to a question like this. And maybe they did come up with them kind of separately, but then somebody investigated them thoroughly and realized there was a deep connection. From that deep connection arose a bunch more of them. Okay, so I think that was what I wanted to say about the measures of center. These are all, at least all the ones we covered, are all tied together by the fact that each of those measures of center is a choice to minimize some objective function on the basis of some choice for a loss function, whether it be absolute value or square or max or something else, logarithm or things like that. Okay, so let's shift gears then to measures of variation, and we'll see this idea pop up later on when we talk about variance. But for now, we're going to shift gears. Moving on to 3.2, measures of variation. And our driving question here is, how spread out or how variable is the data? So if I say had 2 stats classes, if class 1, let's say they took the midterm exam and every single person scored exactly 80%, their average would be 80%. The average score, the mean score, 80%. If in class 2, half of the class scored 60% and half the class scored 100%, the average would still be 80%. The averages are the same, but clearly class 1, if I pick a random student out of class 1, there's very little, in fact, no volatility. There's no variation. Every single person that I pick out of class 1, I'm going to get an 80. If I had to pick one person out of class 2, I might get somebody who scored quite low at 60% or somebody who scored quite high at 100%. There's a lot more variation there in what I could get from picking one person out of that data set. So we see that the mean could be the same, but the spread, the variation, the volatility of the data set could be quite different. So the mean is kind of the measure of center, and the measure of variation is kind of like how widespread the data is. If I plotted these data points on a real line, are those going to cover a wide swath of the real line or a narrow swath or something in between? Our first measure of variation is the range. And the range is nice because it's super simple to compute. The range equals x max minus x min. It's the difference in terms of subtraction between the largest data value and the smallest data value we see. Or if we have our data set ordered, this is xn minus x1. Remember, ever since we started talking about the median, we just put our data set in increasing order. That's kind of the first thing we do before we start working with the data now. So our range is just xn minus x1. It's the largest data value minus the smallest data value. So if I imagine a real line here and I have one data point here, one here, one here, something like that. I see that my data covers a swath of the real line from 1 to 4, and my range would be 4 minus 1 equals 3. Note that the range is not like an interval 1 to 4 or something like that. For these measures in chapter 3, we want to report one number. So my range is 3. In other words, the width of the interval covered by my data is 3 units. So if we come back up here to, let's say, the Ashley and Brandon data, if I can select it, there we go. And as an aside, the range, to my knowledge anyway, never really gets a special notation. So the range for Ashley is her largest data value, 11, minus her smallest of 5 is 6. And remember, this is in units of returns per day. 11 returns per day minus 5 returns per day is 6 returns per day. Our range is in the same units as the original data. Again, that's something that we want to be true. We saw that in our measures of center. Each of our measures of center gave a result that was in the units of the original data. We want that to be true of our measures of variation as well. The range for Brandon, his maximum data value is 14. His minimum is 3. His range is 11 returns per day. Right. Remember, Ashley and Brandon had the same average number of returns per day at 8 returns per day. But we see that Brandon's performance is much more variable. Maybe Brandon, like if he didn't have his coffee that morning, has a really terrible day. And if he had a couple of espressos that morning, he's just gung-ho. Or maybe Brandon kind of has a wider array of complexity of tax returns. There could be different conclusions that could be made off of this, but we can see from the data that Brandon's performance is more variable than Ashley's. If Ashley has kind of the same type of tax returns to do day after day, or if she's just more consistent in general, then even though their performance on average is the same, Ashley is kind of more consistent, more dependable. Brandon is either shows up or kind of misses the mark. For the salary data, so range for the salary data, again, just putting a little subscript A, B, or S or something because I have different data sets that I'm working with here. My maximum data value is 100 minus my minimum of 25, 75, and that's in units of $1,000, again, units of the original data. So again, if my range is one number that represents the width of that interval, say from 25 to 100, it's not the interval like 25 comma 100 or something like that. It's the width of that interval, or it's x max minus x min for the range. Folks can get this confused with mid-range a little bit. Note that the range is not the mid-range, which is x min plus x max over 2. Sometimes folks can get the wording confused, right? Mid-range is a measure of center. It's the average of the extremes. It's the middle of the range, in a sense, the middle of the interval that gives rise to the range. The range is a measure of variation. It's the difference of the extremes. It's the distance between the extremes. So related ideas, which is why they both kind of have the word range in them. But one is a measure of variation, one's a measure of center. So just try not to get those two conflated. So the range we can see is pretty easy to calculate. The range does kind of have a downside though. Let me draw out kind of two distributions for you. One of them has one data point here, one data point there. So it has a few outliers, but the majority of its data is in here. Now, if I look at this data set, if I pull a random data point, I'm probably going to get one that's fairly close to the mean. Let's call it X bar or the median, or mid-range, something like that. I'm probably going to get a data point with a value that's close to the middle, close to the typical data point. There doesn't seem to be a ton of variation in this data set. If I instead had a data set that looked like this, I don't know if that's the same number of data points or not, probably not, but I think you get the idea, where kind of all of the mass is out at the two ends. In this case, I guess I have about the same mean, right? About the same measure of center. But if I pull a random data point from this data set, I'm probably going to get one that's really far one way or the other away from my mean. But what's my range going to be? In both cases, my range is going to be the same because those extremes are at the same place. So the range is easy to compute in a sense because it only touches, or it only considers, two of these data points. That's kind of what makes it easy to compute. I only have to look at two numbers. But its big downfall is that it only considers two of those data points, right? It doesn't care about what all of the rest of the data set is doing. This is a pretty significant downfall of the range. But it seems to get at the idea that if there tend to be data points that are farther away from the mean, they're kind of in a sense going to be farther away from each other, and they're going to be more spread out. Can we develop a similar idea where maybe we take each data point into account so that we can tell the difference between, say, data sets that look like the first one here versus the second? And that's where the variance and standard deviation come in. So the range is important mainly because it's just super easy to calculate. But the variance and standard deviation are a step up in difficulty in terms of how to calculate them, but they have the huge benefit that they're going to touch every data point in the data set, and they will be able to, the variance and standard deviation will be able to tell the difference between, say, two data sets like these. Okay. So let's kind of draw out a real line. Let's draw out just some data points above certain, like this data point is at, this has value at this location. We have another one here. I'm going to draw these at different heights, though. I'm not going to draw them all at the same height, just to make it easier for me to show something graphically in a little bit here. So I don't mean to imply that there's two data points here. I just mean to, I'm just putting this one a little higher up so I can draw something later on. Maybe I have another data point. I'm not intending to space these out perfectly, but maybe I have one here, one here. Maybe I'll put like two of them close together. So here I have 8 data points. Here's X1, X2 through X7, X8. I have 8 data points here. If I were to compute the mean, X bar, yeah, the mean would probably be something like here. Now, if my data is more spread out, wherever I kind of stick a goalpost, or maybe not a goalpost, but a measuring post, I put a flag in the ground, I can measure from there on out, away from there. And the further that things tend to be kind of away from that flag in the ground, if it's kind of roughly in the middle of the data, then generally the more spread out the data are going to be. So if I imagine that up here, right, my typical data point is pretty close to X bar, even though there are a couple that are far away. Whereas here, most of them are pretty far away from X bar, even though there's a couple that are close. So I could imagine thinking about a distance like this distance being X bar minus X1. Or a distance like this, which would be X bar minus X2. And I could think of just adding up these distances. In other words, I could think of variance being maybe something like X bar minus X1 plus X bar minus X2, and so on out to X bar minus X8. Now I notice a couple of things I might want to fix. The first is that the variance, well, if I'm thinking of this being a sample variance, as I take bigger and bigger samples, my population has a variance that's kind of an indication of how variable that population data is. As I take a bigger and bigger sample, I should approach that population variance, but it seems like my variance is just growing, right? If I take a bigger sample, I just have more terms to add on here. I'm just increasing my variance. That seems kind of strange, right? If I take a sample of size 20, it's like pretty much essentially always going to have a bigger variance than a sample of size 10. I think as I take bigger samples, my variance should start zeroing in on something like the population variance. It shouldn't just keep getting bigger. So instead of X8 over here, let's just call this Xn now. So maybe I want to take, the average. So these are deviations. These are deviations from the mean. So I can compute each deviation from the mean. I can compute the sum of deviations from the mean. But it's probably better to compute the average deviation from the mean. So that way, if I have a sample of size 10 or 20 or 100 or 1,000, I'm scaling out the size of that data set. So computing the average deviation from this seems pretty good. We have one little detail though. If I stopped here, what does this look like? Well, let me rearrange this numerator. In this numerator, I have X bar plus X bar. I have a plus X bar in each of n terms. So I have n times X bar minus, the minus factors out of all of these. This is all over n. I can break this fraction up. My n's go away, and I have X bar minus the sum of my x's over n. That's X bar. I end up with 0. Why is my variance or my candidate for variance always 0? Well, the reason is if I do like x bar minus x1 and x bar minus x2, once I get to say x4 in this case, then x bar minus x4 is actually negative. So here I need to switch and do x4 minus x bar or x5 minus x bar. I need to switch the order once I get past x bar. So these represent signed deviations from the mean, and I want them to be absolute, in a sense, deviations from the mean. One way that I can actually fix this is I could just slap absolute values on here instead of parentheses. So can we just use absolute values? And the answer actually is essentially yes, we could do that. We're not going to go that route, and there's a couple reasons for that. The main reason has to do with what I mentioned up here, that the idea of taking absolute values of things ties to the median, and the median is not the measure of center that we want to really deal with here in the variance. We're going to see why that is later on in like chapters 6 and 7, but it turns out that the mean is a much nicer measure of center to deal with, looking at kind of long-term strategic goals. We have an important theorem that says something really important about the mean. We don't have a theorem like that about the median. So we really want to focus on the mean. But what's the mean's kind of underlying function? It's not absolute values, it's squaring things, right? One way we could take these numbers that are sometimes positive and sometimes negative and turn them all positive is to take an absolute value. But we don't want to do that because that would be associated with the median. That's really not going to fit our long-term strategic goals, namely moving into chapters 7 and 8 and trying to come up with decision-making strategies. What we'd rather do is use squaring because that is related to the mean. So we could actually develop something like this related to the median. It would be called something like the median absolute deviation or the mean absolute deviation, where x bar would be replaced by median, the parentheses would be replaced by absolute values. That's an okay thing to do, but it doesn't serve our purposes. So we're going to come through and square each of these. Taking a negative number, squaring it makes a positive. A positive number squared stays positive, and 0 squared is just 0. So we've effectively done a similar thing to what the absolute value does, but we've done it in a way that's consistent with the mean, that's consistent with the ideas that we're going to need for later on in the course. Once I'm adding up a whole bunch of positive or non-negative things, this is no longer an issue. This is always a non-negative number, and it's 0 if and only if every one of my data points has exactly the same value. Okay, so this was basically scratch work. I wanted to show you where the idea of the variance comes from. We want to do something like taking the average squared deviation from the mean. So let's restate this a little more cleanly now. The variance is the average, and I'll put that in quotes. We'll see why in a second. Squared deviation from the mean. We find our mean, we find x bar or mu. For each of our data points, we compute a deviation from the mean, how far it is away from the mean. We square that number, making it positive or at least non-negative. and then we average it in a sense. Since the variance is so important, again, it's going to be used a lot in chapters 6, 7, 8. We give the variance some special notation. So the population variance gets the notation here. We have a Greek lowercase sigma. This is the type of sigma that's in the middle of the word. If it was at the end of the word, it would look like that. And that's obviously where our S comes from, but this is the Greek lowercase sigma in the middle of the word, squared. Note that this entire thing, we think of it as just a single character, sigma squared or sigma superscript 2. We call it sigma squared. We think of it as a single character that denotes the variance. The superscript 2 is obviously a nod to this superscript 2 up here, this squaring that we did as an essential part of computing this. So sigma squared is defined as, well, here we're dealing with a population. So instead of X bar, I think I want to use the population mean mu. Note that it doesn't really matter what order I write these in, whether I write X bar minus X1 or X1 minus X bar. Once I square it, switching those, the only effect that would have is a factor of -1, but that factor gets squared off. So I want to take each of my deviations from the mean. I want to look at the squared deviation from the mean, and I want the average of the squared deviations from the mean. So I have n of these terms. I divide by n. That is my definition of the population variance. Sigma squared, it's the deviations from the mean, xi minus mu, the squared deviations from the mean, xi minus mu squared, and the average of those, meaning add them together, divide by n. And we are going to go through examples of computing these, and so we're just working out the definitions right now. I think it's important to work out the definitions this way to show you where they come from, to show you why do we have something that's seemingly this complicated. But I think if we skipped any of these steps, any of these complications, when we go back to first principles, we're not really doing justice to the answer we're trying to provide. Okay. We also have a sample variance. It's denoted S squared or S superscript 2. Here we're dealing with a sample, so our mean is going to be denoted X bar. And at this point, everybody in their right mind would say divided by n. We take the average squared deviation from the mean, just like in the population variance. We have this minor issue, though. We have a sample statistic, and it's estimating a population parameter. We'll talk a little more about estimators and things in chapter 7, but for now, I think we intuitively understand that what we would like to know is sigma squared. If I had access to the whole population, I would just compute sigma squared and I'd be done with it. I have the population variance and I would be happy. But again, we're usually stuck with dealing with a sample, even though we want to know the population parameter. So I need to compute a sample statistic. And my hope is that when I compute that sample statistic, it's in some sense kind of close to the population parameter. What do I mean by in some sense close to? Well, that might be a little bit complicated, but at the very least, I would hope that it's kind of on average equal to the population parameter. In other words, if I went out and collected a sample of size 100 and computed the sample variance, and you went out from the same population, you collected a sample of size 100, you computed the sample variance for your sample, and maybe each one of us in this class did that. If we did something like average the sample variances that we got, we would hope that that average would be pretty close to the population variance. If that wasn't true, remember back in chapter 1, we talked about estimator bias. If we computed our sample variances in such a way that when we average lots of them together from lots of independently taken samples from the population, if that average tended to not be equal to the population variance, we would have bias in our calculations. Unfortunately, if we compute the sample variance this way, in an analogous way to the population variance, we actually introduce bias. And it turns out that we have to subtract 1 from the denominator. This seems like an absolutely silly thing to do. I completely admit that. But if you go through the math, which is beyond the scope of this course, this is what gives an unbiased estimator. I have a PDF that I put together that kind of works through a tangible example to kind of show empirically that this is a reasonable thing to do. So I'll post that on Blackboard. It's called Y divide by N-1. So you can kind of see through kind of a worked out example that this actually does work. But kind of the proof in general is beyond the scope of this course. So for sample variance, we have to do this minor correction. The computation is almost the same, just with N-1 instead of N. Okay, so let's come up here to the Ashley and Brandon data. And recall that these were populations. Again, there's no way that you could tell that just by looking at the data, but somewhere up above I said that, and that piece didn't copy down. So let's compute the population variance for Ashley and Brandon. Now that we have a bit more computation to do, when we were doing measures of center, the computations weren't all that involved. But here I think we see that we're getting to a point where the computations are a little more involved. I want to organize things a little bit. And this is the way that I like doing it. So let's start with the Ashley data. I'm going to make a list I, in other words, the data points number, the first data point, the second data point, and xi, its value. So I goes from 1 to 5 for the Ashley data. There are 5 data points. And remember, I'm going to order these. So I'm going to take the smallest, 5, then 7, then 8, 9, 11. If I do this at the very first step when I want to calculate something, if I want to calculate the mean or the median or something, if I just do this right away, I've already got this set up, and I can see that this can help me find, say the mid-range or the range. I can pretty easily find a median. Everything's ordered already. I could find the mean, the median, the mid-range, the range, all of those things pretty quickly. For the mean, what do I need to do? I need to add up my xi's. Sum is 40. And then in my mean, mu a is 40 over n, which is 5. I can easily find my n as well because I've enumerated each of the data points. So Ashley's mean is 8 returns per day. Again, we found this before, but in this chart, it makes it maybe a little bit easier to find. I'm going to work off of this chart. I'm going to append some columns to help me compute my population variance for Ashley. So now my goal, find the population variance for the Ashley data set. Again, I have an average squared deviation from the mean. So what does that mean? That means I need to find deviations from the mean. I know the mean already. I did that just prior. So I know the mean, so I can now compute deviations from the mean. Then I can square them, then add them together and divide by n. If I break it into little steps like this, it's not so bad. Some folks like to write out this whole fraction up here. I think it's just so easy to make a little mistake if you do that. Some people like to use summation notation, like sum of xi minus mu squared, like that. I think, again, it's really easy to make a mistake with all of this extra notation floating around. That's why I like to just kind of write everything out a little more explicitly and see what we need to do. We need to first compute the deviations from the mean, then square them, and then average them in the sense that I need to add them together and divide by n, or possibly n minus 1 in a different case. So first I need my deviations from the mean, xi minus mu. 5 minus 8 is -3, 7 minus 8, -1, 0, 1, and 3, just going down the line here. Something that you might remember from above, remember that the average deviation from the mean should be 0 before I squared it, right? That should be 0. But the average is 0 if and only if the sum is 0. One thing I could do to check is I could actually verify that this column sums to 0. If I rounded, it might sum to like, 0.2 or maybe like 1 or -1 or something like that, but it should sum to a number that's pretty close to 0 relative to the size of the numbers in the column. And I see that this sums to exactly 0 because I haven't rounded anything. So that's just kind of a check that I did this arithmetic right. I have my deviations from the mean now. The next step is to compute these squared deviations from the mean. That just means taking each of these numbers in the previous column and squaring them. 9, 1, 0, 1, 9. So these are my terms. Like this term would be 9, and then 1, and then 0, 1, and 9. These are the things that I want to average together. In other words, that I want to add together and then divide by n. The sum of these is 20. Sometimes we call this the SSD, or the sum of squared deviations, and implied is from the mean. So if I refer to the SSD or sum of the squared deviations, that's this sum here. It's the numerator from up here. The numerator up here is by far the hardest piece to calculate, right? It has all these pieces to it. And that's what we have here. That numerator is 20. We've done in a couple of columns, we've done the hardest part by far of really any of the computations in chapter 3 as a whole, I would say, but certainly in this population variance. So then sigma squared for Ashley is 20 over n. And again, I can find n quickly by just looking up on my index column over here. What's the largest index? It's 5. Ashley's standard deviation is, or sorry, Ashley's variance. I'm sorry, I jumped to the next section. Ashley's variance is 4. Any questions so far? Oh, I see there's a couple in chat. I didn't have my chat window popped up, so okay. Yeah, so hopefully this is giving you some more practical application for the computation. Just answering. Oh, that was a DM, but yeah. So hopefully we'll work through 2 more like this, the Brandon and the salary data, and hopefully this will give you a little more work on actually computing things rather than the more theoretical background. So let's do the same for the Brandon data. Let's see, can I just select this and have it come down here? Good. Having a good tech day today, so keeping my fingers crossed. I don't know what it is with OneNote, but OneNote seems to either be really happy to copy things perfectly, or you like copy and paste and it like blows everything up. So again, I want to start by organizing my data. I see I have 5 data points, so I'm going to just write out my index column, 1, 2, 3, 4, 5, just labeling the data points. I'm going to start with my lowest, work up to my highest. And again, at this point, I can easily find any of my measures of center. I've already got them ordered, so things like medians and mid-ranges are easier to find. Things like the range, our first measure of variation, is easy to find. And X bar is easy to find. We sum the column. That's 40 returns per day. And then the average mu for Brandon is 40 over 5 is 8 returns per day. Just like with Ashley, I'm going to do the same thing for the Brandon data. I'm going to find my deviation from the mean, square it to get my squared deviations from the mean, add those together, divide by n in order to average those squared deviations from the mean. So the deviations from the mean, 3 minus 8 is minus 5, minus 3, minus 1, 3, and 6. As a check, I remember that the sum of this column, before I've squared or taken absolute values or anything like that, this should sum to 0. I get minus 9 plus 9, that does sum to 0. That's a nice, just little check that I can do to make sure that things are working the way they ought to. Again, if I rounded my mean or if I rounded any of this, then I might have a little bit of rounding error. But with numbers this size, I wouldn't expect an error like 5 or something like that, right? If I got 0.1, 0.2, negative 0.3, yeah, that's close enough to 0, even if I had rounded or had needed to round. So I have my deviations from the mean. I want to now find my squared deviations from the mean. This is 25, 9, 1, 9, and 36. This is each of the terms in the numerator, or this is these are the 5 numbers that I want to average together. So I can find the sum. Remember, this is the SSD, the sum of the squared deviations from the mean, the numerator of the variance. 25, 35. This is adding 9 gives me what? 44. Adding 36 gives me 50 plus 30 is 80. So my numerator on my variance is 80. And then my variance, sigma squared for Brandon, is 80 divided by, again, number of data points divided by 5 is 16. So actually his variance was 4. Brandon's variance is 16. That's kind of in line with the range, right? That's in line with the range for the two of them. Brandon's data set had a much larger range than Ashley's. Brandon's data set has a much larger variance than Ashley's. Brandon's data is more spread out. Okay, and then lastly, what about the salary data? Let me pull that data set down here. And super important, our salary data is a sample. So now our goal, find S squared for the salary data. And again, I want to start by organizing my data. I see I have 1, 2, 3, 4, 5, 6, 7 data points. I'll start with the smallest, 25. Then I have 3 28s, 30, 55, and 100. And let me bring up my calculator here. So let me go down here and add these together. So 25 plus, I'll do 3 times 28 to save myself a little bit of time, plus 30, 55, and 100. Does that look right? Yep. 294, and then divided by 7 is 42. So sum 294, and then X bar, because we're dealing with a sample here, X bar is 42, and this is in units of $1,000. So now let me compute my, I should have made these green to match the ones above, but now let me compute my deviations from the mean, which we're now calling X bar. I'm trying to be careful with mu versus X bar, again, because we now see that it actually does make a difference to the calculation. We'll get a different number if I were to compute a sample variance versus a population variance. So xi minus x bar, 42 minus 25, that's what, 18? 17. 42 minus, well, with a negative. 42 minus 28 is 14. 3 more because this incremented by 3, so this increments by 3. These 28s are the same data value, so I just have a couple more negative 14s. 30 minus 42 is negative 12. 55 minus 42 is plus 13. 100 minus 42 is plus 58. So I see I have 68, 69, 70, 71. 14 times 3 is 42. And plus 12 would be what, 54. And plus 17 would be 71, and that's with a negative. These do sum to 0. So that's a good check for my arithmetic. These aren't actually, these were just used as a check. I'm not going to square those. Just this first column here that I square this, negative 17 and so on. I'm going to go ahead and square each of these. When I square them, the negative squares off anyway, so I won't worry about typing in negative 17 squared. I'll just type in 17 squared. 289. 196 for the next three. 12 squared is 144. 13 squared, 169, and 58 squared, 3364. I would like to add these up. So I have 289 plus 3 times 196, 144, 169, and 3364. Oops, I missed the 3 there. All right, 289, 3 196s, 144, 169, 3364. That looks good. This gives me 4554. Again, this is our SSD, sum of the squared deviations from the mean. This is our numerator. Up here. It's the same process as the Ashley and Brandon data. The numbers were just a little bigger, so it was just a little more computation and use of the calculator, but same idea. Now, S squared is 4554 over 7 minus 1. Again, I want to be really careful that I don't do something like this over 7 minus 1. Again, the calculator respects order of operations. This will take 4554 over 7, figure out what that is, and then subtract 1 from that. If I'm going to plug directly in the calculator, I need to use parentheses, or I could simplify it to 4554 over 6 and then type that in. That's fine too. But this gives me 759. A couple of things that I notice about the variance. One thing that I really noticed in the salary data is, remember we looked at this before when we were looking at, say, outliers or skewedness. We looked at the way the measures of center lined up, and we kind of said we kind of think that 100 is an outlier, maybe a right outlier, maybe indicating some right skewedness because of the way the measures of center lined up. And we noticed that by far the biggest contribution to the variance is from that outlier. All of these other contributions are like on the scale of less than 300. And this outlier's contribution is on the scale of 3,010 times the contribution or more of all of the others. It's an order of magnitude larger. But 100 is maybe 2 or 3 times as large as the other data values, at least most of them, right? So my outlier is 2 to 3 times as big as the other data values, but its contribution to the variance is like 10 times the size of the other data values. So why is that? Well, really why that is because of the square. If we had just taken absolute values of differences, then if something's twice as far away, its absolute value is twice as big. If we take squares of differences, something that's twice as far away is 2 squared or 4 times as big. So if this is 3 times as far away, its contribution is going to the variance is going to be 9 times as large. If it's 5 times the size, its contribution to the variance is going to be 25 times as large. This square means that outliers disproportionately impact the variance. So outliers have a huge impact on the variance. Very important qualitative thing to understand. In the presence of outliers, your variance gets very large very fast. Now, another thing that we have really shied away from talking about is units, right? I mean, I didn't really track the units through. Let's go back to the Ashley data and track the units. The original data are in returns per day. The mean is in returns per day. Therefore, the difference between them, their deviation is returns per day as well. But when I get to the squared deviation, I have like -3 returns per day squared is 9, but that also squares the unit. This is in units of returns per day squared. The sum of the square deviations, the numerator of the variance, is in units of returns per day squared. And the variance itself is in units of returns per day squared. That's kind of unfortunate, right? All of our measures so far have been in terms of the original units. So I kind of knew what I was talking about. I know what a return per day is in the mean or the median or the range. I don't know what a return per day squared is. Even if this was a unit that I could kind of connect the square to, maybe I was measuring something in inches and then I got square inches out, I might say, okay, I kind of get an idea of what square inches is, but inches is a unit of length. How does square inches relate to length? How does a unit of area relate to length? That connection has been severed. So even if I maybe understand what square inches are in maybe a different application, it's not clear what that means in this application. The same thing would be true with the Brandon data and of course with the salary data. The original data are in units of $1,000, the mean in units of $1,000, the deviations themselves in units of $1,000. But because of this square, or this would be like 1 million square dollars. Like, what is a square dollar? That doesn't make any sense. So the variance, this idea of something like the average squared deviation from the mean is a really nice idea. It's a very important idea, but it has this downside. A lot of the math works nicer with the variance, but we get these crazy units out. We get square units out. And I really don't want square units. That's where the standard deviation comes in. And the good news about the standard deviation is we've done all of the heavy lifting to get there. This next step is pretty simple. The standard deviation has some notation as well. The population standard deviation is denoted sigma, and the sample standard deviation is denoted S. And it's simply the square root of the population variance or the square root of the sample variance. When I square root a number with a unit, I square root the number, but I also square root the unit. Since my variance had square units, once I square rooted, I'm back to units of the original data. The standard deviation has units of the original data plus the benefits of the variance. So the standard deviation, in a sense, kind of touches all of the data points. It has this idea of squared deviations from the means embedded in it, but it also returns us back to the units of the original data, back to nice units. So for instance, the standard deviation for the Ashley data is the square root of her variance. Her variance is 4 returns per day squared. Or 2 returns per day is the standard deviation of the Ashley data. This is a measure of variation that has all those benefits that we built into the variance, considering each of the data points and so on. And it has units of the original data. So my units are back to normal. The standard deviation of the Brandon data's variance was 16 returns per day squared. So this is 4 returns per day, again, units of the original data. And the standard deviation for the salary data, the process is exactly the same. We have a sample standard deviation now, so we call it S. It's the square root of 759, and that unit was thousands of dollars squared. Well, let's come over to the calculator, figure out what is the square root of 759. That gives us a number about 27.5. So we'll round this. And this is in units now. The $1,000 squared gets square rooted units of $1,000. Again, back in units of the original data. If we want to understand something about the data set from a measure of variation, we're typically going to want to look at the standard deviation. If we want to do calculations and things later on, it's actually often better to work with the variance when you're doing calculations, when you're trying to, work with some of the material in, chapter 5 or some of the proofs that we'll do. A lot of times it's easier to work with the variance because once you throw the square root on things, that non-linearity of the square root kind of makes a lot of things difficult to do. So a lot of times we can make nice mathematical statements about the variance because it is not sitting under a square root. But when we want to report a number, when we want to understand something about a data set or a population or a sample, a lot of times we want to report the standard deviation because that's more intelligible of a number. Math works nicer with the variance, understanding works nicer with the standard deviation. So it's important to kind of to know and understand both of them. And they're just related by one being the square root of the other. Are there any questions on anything up to this point? Okay. Let's come over then to our Excel file. So this is on Blackboard, and I sent it out in chat last time. So this is the file we worked with last time. Ashley, Brandon, and salary data. I'm going to go through once again from first principles a little more quickly than last time to compute our measures of center, but also to go ahead and compute our range, variance, and standard deviation. I'm going to name each of these data sets. So I'll select the Ashley data, come up here, and I'll just name it something like A data or Ashley or whatever you want to name it. I'll name this B data. I think I had already named it Brandon maybe, but. And then this one, S data for salary data. And again, to compute the mean, I use equals average. Remember, we have to start with an equals if we want to compute something. Average is the function, the built-in Excel function that I want to call. And the input into average is going to be my Ashley data. I can verify that that's the right data set and it looks good. And I'm going to copy these across and down. Oh, my border copied as well. I didn't want to do that, but it doesn't really matter. And I'll just come over here and double click. I want to change that to B data. And I want to change this to S data. And I want to change this function to median in each of these three. I don't know if this saved me a whole lot of typing. Well, I should have copied it. I should have made my changes and then copied it down. So it actually didn't save me any typing because I missed a little step there, but there we go. Did I actually get all of these? Maybe I should have just typed them in from scratch. Average of A data, median A data, average and median of B data, average and median of S data. That looks good. The mid-range was max of A data plus min of A data close the parentheses and divide by 2. I hit caps lock by accident at one point instead of tab, and then that messed up my typing. Let me drag this across. I want to change these A datas to B data. And then to S data. So if you don't goof it up like I goofed it up, it's actually pretty efficient to go through here and make these changes, but I forgot to change my A, B, and S before I drag down and got a little antsy about dragging down. So, but here are my measures of center. And then for my measures of variation for range, there's not a built-in Excel function, but I can use the same functions, max and min, max of A data minus min of A data. And I don't know why Excel like insists on lowercasing my D for data, but like when I go back, it's not lowercase. So same for the range for Brandon. Max of B data minus min of B data. And for salary, max of S data minus min of S data. This gives me my ranges. And here's really where the time savings really comes in variance and standard deviation. So the function for variance in Excel is just VAR. If we look down here, though, we see that there's two different subfunctions of VAR. And unfortunately, I can't make this bigger, but you should be able to see it on your screen. VAR.P calculates the variance based on the entire population. VAR.S estimates variance based on a sample. VAR.P is the population variance up here, sigma squared. VAR.S is S squared with this -1 on the bottom. With this, like 7 minus 1, which would be 6 in the denominator. Since the Ashley data is a population, I'm going to use VAR.P of the Ashley data to compute the variance, the population variance of the Ashley data. And I get 4, which is what I expected. Same thing for the Brandon data. I'm going to use VAR.P. The Brandon data is also a population, we were told, of B data. That's the 16 that we got by hand up here. And for the S data, VAR.S, because the salary data is a sample, and that is the 759 that we got by hand. And the standard deviation, we could either calculate it as the square root equals SQRT of the variance. We could do that if we already had the variance. Or we could calculate it as STDEV. And I see for STDEV, there are two subfunctions, STDEV.P for population, standard deviation, or .S for sample standard deviation. The Ashley data is a population, we'll use .P. And we see we get our 2. Again, STDEV.P for the Brandon data, because the Brandon data represents a population. We were told that. No way to know that just looking at the numbers, but that's given to us. And then for salary, STDEV.S. The salary data is a sample, and that gives us our 27.5 or so for the salary standard deviation. My general recommendation on the homework is if you have a data set that's less than 10 data points in size and where the numbers aren't crazy, where it's not like, thousands or something like that, or where you don't have like, 28.57 or something. If you've only got a couple of sig figs of accuracy in the data, and if you have less than 10 data points, I think it's a good exercise to go through these all by hand. If you start to get up to the point where you've got more than 10 data points, or where the accuracy of your data is like 3, 4, 5 significant figures, it's much. And as an aside, when I say by hand, I mean a combination of like writing it out and calculator. So not like, squaring whatever numbers we had to square for the salary in your head, but by hand, I mean paper and calculator. When you start to get up to bigger data sets, 10 or more data points, or larger numbers that have, more digits to the numbers, you're going to start making mistakes when you do anything by hand. I'm not just saying you, anybody is going to start making, goofy little errors, copying things wrong. When you get up to, maybe 10 or more data points, I would definitely switch over to Excel for variance and standard deviation, especially. You can still kind of do, the mean, the median, more or less by hand up until maybe 20 data points or so. But certainly after you get past maybe a data set of size 20, I would even do the measure the center on Excel rather than by hand and calculator. So most of the problems on the homework are in that kind of smaller data set range. Most of the problems on the homework, I would recommend doing the measures of center definitely by hand. and the measures of variation by hand. But once you get up to the point, again, where you're, pushing 10 data points or more, or the numbers are like 3, 4, 5 significant figures, something like that, definitely at that point, come over to Excel to do the measures of variation. And if you're going to go through the hassle of getting the data into Excel and all that, you might as well do the measures of center in Excel as well. So I think in each of the sections, there's maybe 1 or 2 problems near the end of the homework that's just a little more data intensive. And I don't want you to do those ones by hand. My strong recommendation is to not do those by hand, but to come over to Excel. But for the earlier ones with smaller data sets, with easier to work with data, you should do those ones by hand, just to go through the motions to see how everything works out, right? Going through a table like this, you'll catch things like seeing this, oh, this outlier contributes very substantially to my variance. That's something that I wouldn't have seen if I just came over here and typed this formula in, right? I wouldn't have noticed this about this data. So there are some things you'll notice or learn about the topic overall by going through some of these problems by hand. But then whenever it gets cumbersome, come over to Excel. Use, like I often say, use technology as a tool, not a crutch. And that's what I mean by that. That in theory, you could do it by hand, but you choose to use Excel or you choose to use a calculator because it's more efficient and less error prone. Okay, a couple questions in the chat. Yeah, so can we do the range again? Sure. Just like mid-range, how mid-range is max plus min over 2, range is very similar in that it's the maximum value minus the minimum value. So we just do maximum of the data minus the minimum of the data. There's not a built-in Excel function to find the range, so we just do max minus min using those 2 built-in Excel functions, combining them together with subtraction to get the range, or averaging them to get the mid-range. Any other questions? Okay, great. Okay, so then let me switch my share back over. Okay, a couple minor points to wrap up in section 2, and then we'll start section 3 next time. We have another measure of variation called the coefficient of variation. The good thing about the coefficient of variation is it's really just a simple relationship to things we've already computed. It's a measure of variation, so we want it to get bigger or smaller as our data gets more or less variable. But the idea of the coefficient of variation is to kind of scale out the size of the data. If I look up here, the Ashley and Brandon data are have units, first of all, of returns per day, whereas, say, the salary data has units of thousands of dollars. We also see that those data sets have just kind of in general a different size, right? $42,000 or 42 versus, say, 8 for their means, for instance. Or I could even think of, like, I could have, in a different problem, presented the salary data as 30,000, 100,000, 28,000, right? With units of dollars. And then my standard deviation, or my variance, would have been like 759 million. And my standard deviation would have been like 27,500. So I have different fundamental sizes of my data values, and I also have different units. Kind of the size of the data value is, in a sense, kind of an abstract idea of a unit. And I have different explicit units, dollars versus returns per day, and so on. The idea of the coefficient of variation is to scale out the size of the data and the units so that we come up with a unitless quantity that maybe can be more easily compared across different data sets with different scales or different units. So the coefficient of variation is the standard deviation over the mean. It's either S over X bar if we're in a sample, or it's sigma over mu if we're dealing with a population. So for instance, the coefficient of variation for the actually data, actually standard deviation is 2 returns per day. Our mean was 8 returns per day. The unit goes away, 2/8 is 1/4 or 0.25. Her standard deviation is a quarter the size of her mean. The coefficient of variation for the Brandon data is 4 returns per day over 8 returns per day is 0.5. These are unitless quantities. It's just the number 1/2. Brandon's standard deviation is 1/2 the size of his variance, or sorry, of his standard deviation. Or his standard deviation is 1/2 the size of his mean. And the coefficient of variation for the salary data is 27.5 with the unit of $1,000 over 42 with the unit of $1,000. The unit goes away. And let me quickly, I won't bring the calculator back up, but we'll just do 27.5 over 42 is about 0.65. So the salary data looked more variable up here, but it was a little hard to make that call, a little more variable than the Ashley or Brandon data. But it was a little hard to make that call because we had different units, we had different general sizes of the data, of the numbers in the data. But even after scaling that out, we do see that it looks like the salary data is more variable than the Brandon data, and the Brandon data is about twice as variable as the Ashley data. That kind of 2 times variability between Brandon and Ashley meshes with their standard deviations, also kind of nicely meshes with their ranges, 6 versus 11. Note that that doesn't really hold with their variances. 4 versus 16 is a 4x relationship, again, because of that square. 2 squared is 4, the square root of 4 is 2. That's where this that kind of correction, moving from the variance to the standard deviation, comes in handy. So the coefficient of variation is a unitless measure of variation that sometimes can be helpful if we're comparing variation between data sets. So when we come back, we'll finish up one last little topic in chapter or section 2.2, and then start on section 2.3, 3.2 and 3.3. All right.